Stairway to Heaven. Problem statement. We want to reach heaven, that is at the top of the staircase. The staircase has n steps, and at each step we can climb either one step or two steps further. In how many ways we can reach the heaven? An example would help us to understand the problem statement better. Consider a staircase with 3 steps, that is n is equal to 3. We are initially located at the bottom. All we can do is take either one step or two steps. Our aim is to find the total number of different ways to reach the top. Let's say take one step, again one step, and again another one step to reach the top. Or take a big long 2 step at the start and then one step to reach the top. Or perhaps take one step and then a 2 step further to reach the top. These are the only possible different ways to reach the top. And hence, for n is equal to 3, we need to return our output as 3. Let's try to examine the problem with another example. The staircase given here is of height 4. Again, we manually try to list down all the possibilities, which are 1 step plus 1 step plus 1 step plus 1 step, or 2 step plus 1 step plus 1 step, or 1 plus 2 plus 1, or perhaps 1 plus 1 plus 2, or even 2 plus 2. We are actually writing down all the possibilities because it's very useful to observe the solution closely while solving dynamic programming problems. Many times it helps us to figure out a pattern which helps us to build our approach. We'll follow the same strategy every time we encounter a dynamic programming problem. If we observe the solution and the different possibilities carefully, we can notice an important thing. Let's focus on our last step to reach the top. Isn't it either 1 or 2 every time? And yeah, that should be the case because all we can do when positioned at any step is take either a 1 step further or a 2 step further. So basically, among all our solutions, which are 1 1 1 1, 2 1 1, 1 2 1, 1 1 2 or 2 2, the last value is either 1 or 2. It essentially means that we can divide all the possibilities into 2 parts. First division with some starting part and then 1 at the end. Let's name the starting part as A for reference. And the second division also having some starting part and then 2 at the end. Here also, let us name the starting part as B for reference. What are these starting parts? Are these solutions to a smaller instance of the same kind of problem we are dealing with? I would highly recommend you to pause the video here and ponder what these starting parts could represent. It's time to uncover what A and B are. Well, A is nothing else but all the different ways to reach the top of a staircase of height 3 units. You can even check the case where n was 3 which we solved at the start of the lecture to verify it. Similarly, B is all the different ways to reach the top of the staircase of height 2 units. Therefore, the number of ways to reach the top of the staircase of height 4 units can be broken down into 2 parts. Number 1. Number of ways to reach n-1 stair or a staircase of height 3 here. Number 2. Number of ways to reach n-2th stair or a staircase of height 2 here. This relation is the main essence for solving this problem. So let us now state the problem more formally. Ways n means the number of different ways to reach the nth stair. We know now from our previous slide that ways n can be calculated by breaking it into 2 parts, which are by taking 1 step from the n-1th stair and 2 steps from the n-2th stair. As already said, for taking 1 step from n-1th stair, we have to first reach n-1 stair and the number of ways to reach there is simply ways n-1 according to our definition. Similarly, for taking 2 steps from the n-2th stair, we have to first reach the n-2th stair and number of ways to reach there is simply ways n-2. So, the number of ways to reach the nth stair is the sum of both, that is, ways n is equal to ways n-1 plus ways n-2. And in general, we can say that ways I is equal to ways I-1 plus ways I-2, where I should be greater than 1 as this relation is not valid for I less than 1. If we try to investigate this further, we can build a tree like this. As we know, ways n is equal to ways n minus 1 plus ways n minus 2. Similarly, using our formula, we can also say that ways n minus 1 is equal to ways n minus 2 plus ways n minus 3, and ways n minus 2 is equal to ways n minus 3 plus ways n minus 4, and so on. But if we are going to calculate ways n like this, it's not going to be a very efficient way for sure. Why? This is because there are many repetitions occurring. For example, ways n minus 2 is being computed here and here, and ways n minus 3 is being computed both here and here. These repetitions decrease the efficiency of the algorithm. So, what can we do to improve it? It's simple. We'll remember them, or we'll save them when we are computing them for the first time. And whenever we require the same thing again, we check if it's already computed or not. Essentially, what it means in context to our problem is, whenever we compute a certain ways I for the first time, we'll just save it in an array named ways. Whenever we are required to compute any ways I, we first check whether it is present in our array. If yes, we return it. If no, we compute it using our logic and then save it in our array after computing. What do we do here is nothing but dynamic programming. Essentially, the two steps we followed and which forms a crux of dynamic programming are: number 1, writing our solution in terms of smaller solutions for the same kind of problem. We did it when we wrote ways I is equal to ways I minus 1 plus ways I minus 2. Number 2, removing repetitions by remembering them when we compute them for the first time. We did it by making a ways array to remember the already computed things. So, now we write the pseudocode for all of these steps. We name our function as Stairway to Heaven, which takes as input the number of stairs, that is n. We first initialize our ways array that will save all the computed results. We initialize ways 0 and ways 1 as 1. Physically, what it means is that number of ways to reach the top of the staircase of 0 height is 1, because we are already there. Also, the number of ways to reach the top of the staircase of height 1 is 1 by just taking a 1 step. These are our base cases. Now, for all the integers from 2 to n, we just use our recursion formula to calculate ways I. Finally, we return ways n as our output, which is the number of ways to reach the nth stair. Now let's run this code for n is equal to 6. We first initialize ways n plus 1, that is ways array with 7 units. We have ways 0 and ways 1 as 1, so filling them up. Now, for the rest of them, we'll just add the previous two values. For example, ways 2 is equal to ways 1 plus ways 0, which is 2. Similarly, ways 3 is equal to ways 2 plus ways 1, which is equal to 3. And so on, ways 4 is equal to ways 3 plus ways 2, which is 5. Ways 5 is equal to ways 4 plus ways 3, which is equal to 8. And lastly, ways 6 is equal to ways 5 plus ways 4, which is equal to 13. Finally, we return ways 6, which is 13 as our answer.